Hello, this is Brett from SurvivalComms, and today's video is on simple refrigeration principles and restoring this old refrigerator. And today we are at the shop of Jim from Dorite Fabrication. And
hey everybody.
Jim picked this up from, I'll let Jim tell you the story.
So I was at Rural King getting feed for the animals here on the farm, and pulled around back so they could fork it on the trailer for me, the pallets onto the trailer, and this was sitting next to the dumpster. I said, hey man, what's wrong with that refrigerator over there? And he said, I don't know, it quit working. They told us they're just going to replace it. This particular unit was used in Rural King to keep vaccinations for animals. A lot of them have to be kept refrigerated. And so I asked him, I said, hey, if you guys are just going to throw that away, can I have it? And he said, yeah. He goes, I don't care, you can take it if you want. So my hope was to fix this. Got into it, and we found out that it's way overcomplicated. There's a lot simpler way to do this. This thing is so, we'll call this Washington, D.C., politically overstimulated, over-designed. It doesn't need to be this simple.
Energy Star.
Yeah, Energy Star, great. It saves energy because it doesn't freaking work. What we're going to do is we're going to go back to the basics. We're going to go back to how the simple refrigeration works. We're just going to wire this with a mechanical thermostat. We're going to replace a couple of fans in here, and we're going to see if we can just make this a real simple cooler. All right, so refrigeration simplified. Let's just keep it simple, stupid. We don't need to get into craziness here. It's a really simple concept. What you have is a compressor. Compressor is nothing more than a pump, and the pump pumps Freon, and by pumping the Freon, we move heat. That's all it does, is it moves heat. And what it does, if we say that this is the direction it pumps the Freon, it pumps it out of here through a coil, okay? And then from that coil, it goes through a very tiny orifice. So right here, we're pumping it, we're squeezing it, the Freon becomes a liquid. We pump it through this coil, and right here, the Freon gas expands because we shove it through a little tiny hole, and then we pump it through another coil, and from that coil, we go back into the compressor. It's really that simple. All right, so when we started off here, I started wringing out all the problems. I ohmed out the compressor. The compressor ohms out to within specifications. I checked the thermal overload. Thermal overload's good. Checked the start relay, start cap. I put it on my meter. Start cap is within specifications. So that basically tells you that this should run. So what I did is I bypassed all the thermostatic control circuits. Just put 110 volts to the compressor. She fired right up. High side gets hot. Low side gets cold. And what that basically means is that the liquid line is the high side. That's under a lot of pressure. And then high side, when it gets hot, that means the compressor's working. It's pumping the Freon. And then it forms a vacuum on the low side, and through expansion you have a pressure differential which creates your cooling effect. My low side was getting cool, inside got cool. I ran it for about an hour. I got it down to, I don't know, about 45 degrees in about an hour inside the cooler. That let me know that she was doing what she's supposed to do. There was no problems mechanically or electrically in the compressor. So then I started wringing out all the electrical panels that are around front. All right, so to make this a little more simple, this had a display on it that told the temperature inside here. It's probably great if you're trying to keep the temperature for medications. You want to make sure it's consistent and all that. It's a lot overcomplicated for what I'm going to repurpose this for, so I'm okay with just deleting it. Now, around front, you can see there's a whole bunch of control boards here. This was the original 12-volt supply that supplied the LED lighting. I just had a 12-volt wall wart, and I just kind of bootlegged it in to make sure the whole electrical system was working. I know all the LED lights work. This is not going to stay here. There's several control boards. There's one here. There's one here. There's one in there. There's also a control board here. That's a whole lot of control boards for nothing. Now, there's two pieces of this equipment we're going to have to keep. We need them. One, if you look up here, there's a fan. Okay, that fan is important. It's just if you look at it, it's just a little computer fan. And then down here, down below, there's another fan. And one of those fans keeps air moving across the evaporator, and one keeps it moving across the condenser. The trouble is that both of these fans are 12 volts. Now, I could mount a 12 volt power supply and power all those, but then again, that gets a whole lot more complicated. This really can be simple. All right, so here's the two parts I had to order. I ordered two of these fans. These came off Amazon. They're, I don't know, 10 buckish a piece, about $10 each, 110 volt fans, and this simple mechanical thermostat. And the way these thermostat works, this is a real simple one. It's set up for a refrigerator. There's a capillary tube here, and there's two contacts. These are for ground, so don't pay attention to those. All these do is make or break the compressor contact. All right, let's draw a real simple schematic. I know we moved through this fast, and I'll just show you how simple this really is. We have two fans. And one compressor. Okay? We have power coming in. This is wall power. This fan, anytime you plug it in, this evaporator fan comes on and it stays on all the time. Okay? This fan and this compressor are controlled by the thermostat. Let's draw the thermostat. Thermostat is like a big switch. There's our contact 1, contact 2. Connects to line here, and this common comes over to both fans. When it makes contact here, it supplies the compressor and this fan to come on and run. When the thermostat says the temperature has been satisfied, this contacts open up, the compressor and this fan shut off. It's really that simple. So what Brett's doing here is he's just getting in the back. We're taking the little valance panel off the fan. We're going to swap this fan that's in there, that's a 12 volt fan, out for a 110 volt fan. Should be a pretty quick and simple operation.
To save ourselves a lot of heartache on the fans, we're just going to go ahead and reuse. It's only a 1/4 amp, so we're going to go ahead and reuse the original DC wiring. And this is the original temperature sensor that would run to that one circuit board. The power cord itself, what I did was I just took the original plug and the new plug for the fan and just basically tied them together. But what I've done is I've soldered it and heat shrinked it. Okay, we have our interior fan running now on AC power. And we basically pulled it out of the plug, which is this second output on this DC power supply here. And we've just tied it together. And the wire's not getting hot or anything, so it's going to be able to handle the current, and this prevents us from having to pull all this wiring through all this insulation up inside the unit here. Now our right side fan, which runs on the condenser, you can see it runs through this second board here. We're going to go ahead and delete that and essentially tie this in, so whenever the compressor lights up, it's going to light this fan up at the same time. It's easy to see all the gack that gets inside the condenser down here, and we're going to go ahead and blow all this stuff out before we install the new fan. Okay, we have our AC condenser fan installed now, and this power supply here was the original power supply for the LED lighting, and since we no longer need this DC supply for the fan, for the evaporator fan, or the inner fan, I just repurposed this power supply and using the same connectors hooked it up for the LED lighting inside the cabinet. So now we have our LED lighting inside of here with the switch as originally intended, and we didn't have to buy another power supply. Now back here we have our junction block where our AC power makes entrance here. And we have a bunch of superfluous circuits now that we're going to delete a lot of these power supplies. So we're going to go ahead and start lifting those to get those out of the way. I took the power supply for the lights and got it tied down. I chased all the wires back through here, zip tied them down.
All right, so to get this through the inside, we need to bore a very small hole. That's pretty simple. We're going to do it probably back here in the back corner. Why? Well, the compressor's back there. All the wires for the compressor are close. We can keep all the wires nice and short. We'll turn this around out back there if we need to make adjustments to the temperature, and we'll run this this tube, this capillary tube up so it can sense the temperature inside the refrigerator. But we don't want it to short cycle, turn on and turn off quickly, because this does not have much thermal mass. It'll change temperature fairly quickly. So one of the things we're going to do is we're going to make a little nugget to go on the end here. And this little nugget is going to be simple. We're going to turn it on the lathe. We're going to make it out of aluminum. We're going to slide it on here, and all it's going to be is a little piece of solid aluminum. And what that does is it takes a couple of minutes for that aluminum to absorb the heat or get rid of the heat, and doesn't change temperature as quickly as this does. Therefore, the compressor can run for a few more minutes, cool the inside down a little bit more, then it'll shut off, the temperature will normalize, it will turn back on, and that keeps that short cycling that these sometimes have a tendency to do.
Now, would it be possible to use like an electronic heat sink and tie that capillary tube to that heat sink and have the same thermal mass?
Sure. All we're looking for is something that won't change temperature as quickly. Alright, so what we got here is just a little drill bit, and this is the capillary tube on the thermostat. You see it's flexible, we can move it all around, and then we put a piece of heat shrink tube on here. This isn't shrunk down yet. And what we're going to do is just push that through the metal here once we get the capillary tube in place to prevent any chafing and wearing a hole in the capillary tube due to vibrations. And we'll just burn a little hole right here through the... just like that. Allows us to mount the capillary tube back here. The last thing we have to do here is we need to make a little thermal mass piece to go on the end. So we'll go in, we'll get on the lathe, and we'll make that real quick. Alright guys, we're over here at the lathe. What we got is in the 3-jaw chuck, we've got just a piece of aluminum. It's unknown type aluminum. I know it's a weldable alloy because I've used this on some other projects that I've welded it. That's proper English, by the way. Anyhow, first thing we want to do is make a facing cut, which means we want to get a true flat edge on here. We want to drill a hole in the dead center of this piece. This is what's going to put our hole in the center for our capillary tube to go in. Now, not to worry, there is no specification on this. We're just going to drill a simple little hole in there. We'll pull our tailstock out, get our drill bit up here in a safe area so we don't accidentally snap it off. And now really all we got left to do is to kind of, well, we don't really have to, it's the right thing to do, is to kind of clean the material up. I just like to do things nicely in the right way, because we're going to clean this up a little bit. And so, since we're going to have a lot of tool pressure pushing on here, we're just going to make a couple passes and make this look pretty. We don't want this rod to flex. We can see that it's flexible. So we'll bring the live center in here and we'll put it in that little centering bit hole that we started. This is a ball bearing and this will support this. Now we can't push it anymore. We'll change our tool to a different kind of cutter. And again, we're not going for anything spectacular here. This is more a by guess and by gosh method here. Alright, so we got a pretty nice finish. It's a little rough, but then again, you know, we don't really care. What we'll do is now we're going to break this corner with
more surface area.
Yeah, right. What we're going to do is just break this little corner right here because it's sharp from the machining. So the way we'll do that is we'll just take a file. And a lot of times, just for good measure, we're going to part this off. We're going to cut this. The way we're going to part it is we don't want any extra hanging out than has to be, because that causes flexing, and anytime anything flexes, that's chatter, and chatter breaks tools real easy. So what we're going to do, we'll bring this in nice and close like this. We'll start the machine, and we're just going to part this off real nice and easy. Just keep getting smaller and smaller in the center. When it comes off, we're holding it right here on the little Allen wrench.
It's like magic.
It's magic. Here's a little part that we made. What we have here is some heat shrink compound. This is what you put on the back of heat sinks for transistors to make sure there's good thermal conductivity between the two. So we do want heat to transfer back and forth from this to the capillary tube here. So I'm just going to put a little schmoo out here all over the end. You know, like they say, nothing says love like lubrication.
That's right.
Yeah. So
and there is safety and sealants.
Yes. This is just, like I said, it's just a thermally conductive grease. I'm going to put this in here, and then we'll wipe that off. And then what we'll do is we'll just use the same screw that was back there in the case. A little Adel clamp. Alright, so the only thing we have left to do is we'll button it up by finding a ground here and grounding it to here. And then I got to make some kind of little bracket, probably just a flat plate here with a hole drilled in the center. Put a couple of Tech screws into here and use that center screw, and we'll mount that thermostat just hanging out the back that gives us the ability to control the temperature inside. As for now, I'm not going to do that. I want to go ahead and test everything out. Alright, so what we've got here is my thermocouple temperature probe on the back of the coil here, just showing the proof that this thing is actually going to work. It's, I don't know, it's around 85 degrees. I had my finger on the end of that a minute ago, so it read my finger temperature. Here is the plug. We'll plug this in.
Going down, down, down.
Sounds like a bad movie.
Yeah.
I mean a good movie, in a bad way. So you can see it's already down to 41 degrees there. And it'll continue to fall. It'll get down below freezing for sure. If we keep this door open, the condensation will begin to frost up on the coil. And then once the thermocouple over here, once the capillary tube senses that this thing is down below whatever we have the thermostatic dial set to, it'll turn the compressor off. It'll keep cycling back and forth, slowly normalizing the temperature. But you can see we're already down to 30 degrees right there. Now keep in mind, right here is where the expansion is happening of the gas, so it's the coldest right here. It has to go up and through all of this coil to normalize the temperature. This is the coldest part. This is the warmest part of the coil. So here is a mid-temperature. That's why the sensor is on the mid-temperature range there. We're at 29 degrees Fahrenheit. All right, we thought we'd take a little look and see what this thing is pulling current-wise. 2.3 amps, that's including the fans. That's total current consumption running, and this is running when the unit is still very warm inside, so it's working at maximum load right now, trying to cool everything down. So 2 amps, pretty efficient. Well, here is the cooler, and there's still going to be some cleanup action that's going to happen. And right now, after a half hour of running, we're at 38.3 degrees, which is very impressive, although there's no heat load inside of it right now. And you know, what I'm going to do is I'm going to spend a little time. You can see I already peeled off the advertisements on here. We're going to peel the advertisements off the side. I'm going to spend a little time on the glass and clean it up real good, give it a good scrub down and get it ready. Wanted to proof of concept here, wanted to make sure it works. You know, I'm pretty satisfied with that. I'm going to let this thing run out here for a couple of days, keep adjusting the thermostat, keep checking it with the temperature probe here, and make sure that I can get it to a pretty stable temperature inside just by playing with it. Got a few more screws to button up. You can see we put the bottom valance back on the front of it. A few more things in the back to put back on there once we're 100% sure everything's right where we want it. But overall, I appreciate Brett coming out and giving a hand today doing this. You know, for a total of $30 investment, roughly about 10 bucks each for the fans and $8 for the thermostat. I hope we get a couple years out of this for the kids to keep their chicken eggs in.
Okay guys, I hope this helps. This is Brett from SurvivalComms. Till next time.
See y'all soon.